Hello, my name is Alexis, and in this video I'm going to talk about how I built a mini generative pre-trained transformer similar to GPT or GPT-4 that you may already know, and so it implements most of the basic architectural elements of GPT in a more simpler way for learning kind of like the ins and outs of how GPT works. And so to begin, I'm going to talk about the imports. So I just use Torch and I'm using Google Colab environment. And you don't necessarily need the A100 environment, but you can use any other L4 or T4 GPU environment. As long as it has a GPU or even a CPU, it might work. So you have to choose your initial training data, and I used a book called Voices from Within the Veil by W.E.B. Du Bois, and I chose that book because it's interesting and I'd like to read it someday. But it's also open source and you can use it yourself without any copyright. So I got it from Project Gutenberg, and you can get any other book from there, but you can use any text data as well. Since it's a LLM architecture, it's used for building large language models. GPT is able to use text data primarily, and I'm using a Google Drive link so I don't have to scrape the website, and it's a little bit easier that way. So every time you're like running this, you don't have to pull the data every time from the website, and you don't have to worry about getting your data interrupted. And the first step, I guess, would be to check the vocabulary size and the characters within the text, since this is going to be used for not only building the tokenizer here, but also when you're using the model, knowing the characters and vocabulary size helps to set up the model kind of like hyperparameters. So this is a really basic tokenizer scheme, and there are other tokenizers out there and other encoding schemas that are probably better and can help save memory and can speed up encoding and decoding. However, this one is the most simplest to understand and easy to use. It basically just maps a character to an integer, which is the index. So since there's 98 characters, that location would be the index. And then it just creates like a dictionary mapping, and you can reverse it so you can get the integer from, or the character from the index. And then the encoding just retrieves that value for each, and then the decoding just returns the character given the index. And then once the tokenizer is built, then we encode the entire data set and then create the train and test sets. And then after that comes the more complicated part, which is creating the functions to batch the data, create the data loaders, and then creating the model. So to create the data loader, there's some Torch functions being called that creates data batches by stacking the individual batched matrices, and it indexes the data using the block size, which you can set here, and that is also the context length. So if you look down here, there's this tensor, which is a matrix of lists, and each list is considered like a chunk or sentence or a context, and they're of size 8. And right here it's size 8 by 4 since the batch size is 4. and then that is the x on the top, and then the y is on the bottom, which is the target. And you can see that each list within the tensor is shifted by 1. So you can't tell for the first line because they're all 1s, but for the second one you can see that the 61 here was actually at a different location. It was over here, and then it was shifted by 1. 78 was shifted by 1, and so on. So the entire batch for the y is shifted by 1, and that's because the model uses each context to make a prediction about the next word in the sentence, and then that is called like the model's attention, and the model can have multiple attention spans. So there'll be many of these created for like more complicated models where the input is different for each target, and that helps the model understand like grammar and other complicated patterns within the data. So you can see like for the first input they're all 1s, but if you were to look at a different input it would shift a little bit differently. So I'll try running this so you can see. So yeah, when they're actual sentences from the text, instead of just like the first array, which is a simple 1 array, each input context is like a subset of the original sentence. So this is just 1 word and then predicts the next word. And then these are 2 words now and it's predicting the third word. And then it'll continue until the end of that context length, which is 8. And each batch is another context, and it does that same process for each. And the model should be predicting the target here for each context length subset. And then next I'll talk about the actual model. These are the hyperparameters. And one of them that I decided to change was the max iterations, which is the number of steps. I increased it from 5,000 to 10,000 since the data was a little bit more complicated than the original example. And when I tested it, I think I got a little bit better result. And the batch size and block size were also increased from the original example that I showed you here, since the input that I use, which is a book, usually has really long context since it's not sentences but paragraphs or entire chapters. And the other hyperparameters decide like the size of the model, the attention of the model, and if the model is skipping any connections in the model layers, which might help with overfitting. Since we're only training it on one book or one data set, it might overfit because it doesn't have much data to generalize to. So adding dropout will allow to like avoid that. And these are the individual classes that make up the model architecture, which is the head, which is like the simplest component of attention. Then there's multi-head attention, which creates like a collection of these heads. And it also adds the dropout. And then feed forward. which is the simplest neural network class. And then the final one is block, which combines the former classes, including the feed-forward and the multi-head attention. And the block class also contains the forward method, which actually implements the gradient descent algorithm to like update the model weights and learn. So the block is the most like useful, and it kind of like combines everything. And then in the language model, you have a lot of those blocks in a sequential layer using Torch. And then you add some embedding tables, which helps to encode the data. And then the LM head, which captures the attention and allows for like the output of the attention to be used for prediction, and then ultimately used to predict just one feature instead of output too many. And then this is done in the generate method here in the language model class, and the forward method, which updates all the model parameters, not just for the block, but also for the entire model itself. And then finally, this is the estimate loss function, which uses Atom W optimizer here. And this is loading all the model parameters. And the optimizer is used to update the model weights during training in a way that is efficient. And the transformer architecture, since it's using the text data to learn, there's a concept called text completion, which is you input some text and then it will try and use that text and predict a certain amount of words from that text up to some max content length. So when I was testing this, I tested it with the title of the ebook that I used, and I expected it to just predict one word, since the title only has 5 words. So I gave it the input voices from within and expected voices from within the veil. And since the max context is actually 20, it over generated and it returned voices from within the given Ramley line. And that is not accurate, and maybe that could be fixed by lowering the max content or allowing for the model to generate or limit itself to not over generate. And the loss, I noticed it was higher when I used the custom tokenizer, but when I used the GPT-2 tokenizer, it did much better. However, a difference that I had issue with when using the GPT tokenizer instead of the custom tokenizer from the transformers class, the GPT tokenizer, it is unable to update the tokens that were used when I encoded the original data, or perhaps there was like an issue with the forward method where when it's calculating the loss, some encodings were not captured, so they had to be cut off since they were not in the tokenizer's vocabulary. And that led to a lot of outputs where the characters were missing. So instead I used the custom tokenizer to capture the vocabulary from within the data set that I had. So yeah, I think it could be improved by updating the tokenizer to not be like a custom tokenizer, adding like a better tokenization method, and perhaps updating the model and or retraining the model with more data would allow for like more generalization, adding dropout potentially to avoid overfitting. And that max new token parameter, which kind of forces the model to overgenerate instead of eliminating it. So yeah, I think this model could be evaluated more to increase its performance. And I learned a lot from this original notebook that I used to build this experiment. It was a notebook that was really useful for me, and I'll link it in this collab as well. So this notebook was used by me also to implement the Nano GPT or the Mini GPT, and it has more examples as well. So yeah, that would be all, and thank you for watching.